Hey everyone, and welcome to The Explainer. Today, we're diving into a shape that looks super simple, right? 3 sides, 3 angles. But believe me, triangles are holding some of geometry's biggest secrets. So, let's get ready to unlock them.
Yep, you heard that right. Just 3 simple angles, but they hide a whole world of rules and relationships. And in this explainer, we're going to uncover them one by one. So let's jump right in. Okay, so our very first secret is a concept called congruency. Now, I know, it sounds like a big, complicated word, but the idea behind it, it's actually super simple. It's all about finding a triangle's exact identical twin.
So, what exactly are congruent figures? Well, think of it this way. They have the exact same shape and the exact same size. They're like perfect photocopies. You know, like 2 brand new playing cards from the same deck, or maybe 2 keys that were cut for the very same lock. They're just identical.
Here's a great way to think about it. 2 figures are congruent if you could literally cut one out with scissors, place it right on top of the other one, and poof, it disappears. It's perfectly hidden underneath because they overlap completely. Not a single part of the bottom figure would be showing.
Now, this is where people sometimes get tripped up, so let's clear it up right now. The difference between congruent and similar. Congruent figures, remember, are those identical twins. Same shape, same size. But similar figures are more like a mama panda and her baby cub. See? They've got the same shape, but they're different sizes. This is a really key distinction. All congruent figures are similar, but definitely not all similar figures are congruent.
Okay, so that leads to a really big question, right? If we want to prove 2 triangles are identical twins, do we really have to measure and compare all 6 of their parts? I mean, the 3 sides and the 3 angles? That sounds like a ton of work. There's got to be a shortcut, right?
And you are absolutely right. There are shortcuts. And our first master key is something called the SAS rule. That stands for side, angle, side. Let's break down how this awesome tool unlocks congruency. Okay, let's start with the first S. It stands for side. So step 1 is just to check if one pair of matching sides in both triangles is equal in length. If they match up, boom, we've found our first piece of the puzzle. Next up, we've got A for angle. Now, listen up because this is a super important detail. It can't be just any old angle. It has to be the angle that's formed between the 2 sides we're comparing. We call this the included angle because it's kind of sandwiched right there in the middle.
And finally, we get to the second S for another side. We just check if a second pair of matching sides is also equal. If it is, well, we now have a complete side-angle-side match.
And that right there is the magic of the SAS rule. Once you've confirmed you have that side-angle-side pattern, that's it. That's all you need. You can confidently say that the 2 triangles are congruent. Doesn't matter how you spin them or flip them, one is guaranteed to fit perfectly over the other.
All right, so now that we have this awesome new master key, what do you say we use it to solve a puzzle? It's time to put this theory into practice.
Okay, let's take a look at our problem. We've got a diagram here with 2 triangles, and you'll notice they share a common side, AB. We're told that side AC is equal to side AD, and also that the line AB cuts that big angle at the top perfectly in half. Our mission is to prove that the top triangle is congruent to the bottom one.
Let's start our detective work. First things first, we can say that AC equals AD. Now, how do we know that? Well, the problem gave it to us. It was right there in the instructions. So we found our first S.
Okay, next up, the angle. We know that the line AB bisects the big angle, which is just a fancy way of saying it cuts it into 2 equal halves. So that means angle CAB has to be equal to angle DAB. And the reason? You guessed it, it was given. Our A is now officially locked in.
Now for the final piece of our SAS puzzle. Take a close look at the side AB. See how it's part of the top triangle and it's part of the bottom triangle? That means AB is equal to itself, simply because it's a common side. And just like that, we've found our second S. So, let's recap, shall we? We have a side, an included angle, and another side. Check, check, and check. All 3 conditions are met. Therefore, using our trusty SAS rule, we can officially declare that triangle ABC is congruent to triangle ABD. Puzzle solved. How cool is that?
But wait a minute. Hold on. Why did we just do all that? What's the point of proving these triangles are identical twins anyway? There must be a bigger picture here, right?
Oh, you bet there's a point, and it's a huge one. See, proving congruency is like unlocking a door. And what's behind that door is basically a geometric superpower. Its name is CPCTC, and it is the ultimate reward for all our hard work. Okay, so CPCTC stands for a bit of a mouthful. Corresponding parts of congruent triangles are congruent. I know, but the idea behind it is pure magic. It basically means that once you've proven two triangles are twins, you automatically know that all of their other matching parts are also equal. The leftover angles, the third side, boom, they all have to match. It's like this cascade of new information you just unlocked.
So let's use that superpower on our problem. We just proved the triangles were congruent using SAS, right? Well now, thanks to CPTC, we can say with 100% certainty that the third side, BC, must be equal to the other third side, BD. And think about that. This is a brand new piece of information that wasn't given to us at the start. We unlocked it. That's the real power of this whole thing.
Speaking of unlocking secrets hidden inside triangles, let's wrap this up with one last really cool discovery. This is a property that every single triangle in the entire universe shares. No exceptions.
So imagine we could just, physically tear off the three corners from any triangle you can think of. A big one, a tiny one, a wide one, a narrow one, doesn't matter. Now, what do you think would happen if we line up those three angles, putting their points together? You'd see that they will always, without fail, form a perfect straight line. And of course, we all know the angle of a straight line is exactly 180 degrees. This reveals a fundamental truth of geometry. The sum of the three angles inside any triangle is always 180 degrees. Always.
So now you have the keys to congruency, and you know about that 180-degree secret hidden inside every single triangle. It really makes you wonder, doesn't it? What other geometric secrets are just out there waiting for you to unlock? Keep exploring.